From the perspective of an instrument-rated pilot, a cloud is a localized thermodynamic engine with a structural logic driven by the relationship between temperature and moisture. This image shows a high-altitude layer of cirrostratus clouds. The flat, uniform horizontal architecture is the prime visual indicator of a stable atmosphere. In contrast, this photograph shows the heaped structure of cumuloform clouds. This vertical development signals an unstable atmospheric condition. These shapes are the result of physics. A cloud's architecture is dictated by the temperature and moisture profile of a rising air parcel, compared to the air surrounding it. To predict exactly where these clouds will form, pilots calculate the base in thousands of feet by taking the surface temperature, subtracting the dew point, and dividing that difference by 2.5 degrees Celsius. By mapping this formula onto a coordinate plane, we can visualize how temperature shifts across different altitudes in the atmosphere. Mastering this relationship allows a pilot to calculate exact cloud bases and anticipate the stability of the air before ever entering the airspace. We model this using a parcel of air at the surface with an ambient temperature of 17 degrees Celsius and a dew point of 12 degrees. As the parcel rises and expands due to surface heating, it cools at the dry adiabatic lapse rate. During this ascent, two distinct cooling rates are in play. The air within the parcel cools at 3 degrees Celsius per 1,000 feet, while the dew point drops at a rate of 0.5 degrees per 1,000 feet. Because of these differing rates, the spread between the air temperature and the dew point decreases by 2.5 degrees for every 1,000 feet the parcel gains. At 1,000 feet, the internal temperature of our parcel has fallen to 14 degrees, and its dew point has decreased to 11.5 degrees. By 2,000 feet, the two variables mathematically intersect. At this altitude, both the air temperature and the dew point reach 11 degrees. At this intersection point, relative humidity reaches 100%. The parcel is now saturated, and visible condensation begins. A visible cloud base is the physical manifestation of this exact mathematical convergence. At convergence altitude, a phase change occurs as water vapor transitions into liquid droplets. This phase change releases latent heat into the rising air parcel. This injection of heat alters the thermodynamics of the parcel, slowing its rate of cooling as it continues to climb. Inside the cloud, the cooling rate shifts to the saturated adiabatic lapse rate, or SALR. This new cooling rate is significantly slower than the initial dry rate, dropping by approximately 1.5 degrees per 1,000 feet instead of 3. This latent heat release serves as the engine of the cloud, keeping the saturated air warmer than it would be if dry, and providing the buoyant force necessary for vertical development. To determine if this cloud will remain a layer or become a thunderstorm, we must introduce the final variable, the environmental lapse rate, or ELR. The ELR is the temperature profile of the surrounding, non-rising ambient air. Atmospheric stability is dictated by a simple rule. If the internal parcel is warmer than the ambient air, it rises. If cooler, the ascent stalls. In a stable atmosphere, the ELR is weak. The rising air quickly becomes cooler than its surroundings, causing its ascent to stall. This results in the air spreading out horizontally into stratiform layers. If the ELR is steep, the ambient air cools rapidly with altitude. The rising parcel remains warmer than its surroundings, allowing it to accelerate upward. This mathematical relationship creates hazardous cumuliform vertical development. A cloud's size and danger level are dictated by the thermodynamic tension between its internal cooling rate and the external environment. Pilots use a standardized macro-level metric to gauge this stability across an entire region. This metric is known as the lifted index. This calculation is measured at the 500 millibar pressure level, roughly 18,000 feet above sea level. The index is calculated by subtracting the theoretically lifted parcel's temperature from the actual ambient temperature at that 500 millibar level. If the lifted parcel is cooler than the ambient air, the lifted index is positive, indicating a stable atmosphere. If the lifted air is warmer than its surroundings, the index is negative. This signals unstable air and the potential for vertical growth. Checking this index allows a pilot to anticipate cumulonimbus development long before clouds are visible on the horizon. While the lifted index provides a macro view, a microscopic hazard exists within the vertically developed cloud itself. Temperatures below -20 degrees Celsius do not guarantee a dry environment of harmless ice crystals. In the free atmosphere, water vapor rarely sublimates directly into ice. Instead, it must undergo glaciation. Without freezing nuclei to help them organize into crystals, liquid droplets can remain supercooled and fluid at temperatures far below freezing. When an aircraft enters this environment, the airframe acts as a highly efficient freezing nucleus. Upon direct impact, the supercooled liquid droplets instantly crystallize, forming dangerous, jagged layers of structural ice rapidly across the airframe. Understanding the mechanics of adiabatic convergence and glaciation allows a pilot to quantify the invisible risks of the atmosphere.